Okay. Do you remember in Algebra 2, maybe even pre-calc a little bit, where you would come up with a set of constraints, you would have a feasible region, and then you would find the vertices of that feasible region and then maximize or minimize a function? Do you remember that? It was called linear programming. Okay? And this is not our topic here today, but I just want to share a little bit with you. Linear program was actually created out of necessity. And it came out of World War II. We had so many the logistics of production and transporting everything was so complex that they needed a mathematical way to find the optimal solution of either manufacturing or getting stuff over there. So say, for example, if you had a ship that could hold so many tons, had so many square feet, how many cubic feet, and you needed to get food, you needed to get fuel, you needed some tanks, you needed, some trucks and this, that, and the other, to find out what was most going to help the effort, they developed this. And so, because we could talk about, actually what we're going to do in Algebra 2 is we're going to talk about how much stuff we produced. It was nuts. It is nuts how the stuff we created. Like, to haul all this stuff, we made what's called Liberty ships that are 450 feet long. In that 4-year span, we made 2,300 of them, which is crazy. Trucks, we built over 1 million trucks, okay? And at the end, we were making bombers at the rate of 1 an hour, just at one plant. Every 57 minutes, they were rolling off. And it's the comprehensiveness and the effort that was undertaken there is just really, really, really impressive. And one of the things that came out of that from necessity was linear programming. And it's kind of cool to have a mathematical process that is rooted in something that we can hopefully kind of relate to. But anyway, how'd it go last night with the normal lines and tangent lines and Desmos? Anything you want to take a look at? I like stuff like that because it gives you some tools and a method where you can go ahead and, first of all, not only graph different lines that or different curves that you've never seen before, but also gives you a way to confirm that yes, my derivative has some meaning. I do want to talk about one thing from yesterday that I was trying to make sense of myself. So say if you've got some weird function, I don't know, maybe it looks a little something like this, okay? And I personally, let's say if we have some function where dy dx is equal to, I'm going to make it fairly basic, okay, that's the derivative. That's not unlike some of the problems we've had. What I wanted to do, what I was trying to find a way to do, was to do what we've done in the past and say, okay, here's my function, and then my derivative would be like this. I wanted a visual representation of that. Do you remember what we did? Okay. Well, I was thinking, why can't I do this? I was playing around with Desmos. Why can't I do it? Why can't I do it? Why can't I do it? Well, it's because we actually have 3 different variables. And here we've got this x, y coordinate plane, and I'm trying to graph yet another value, x or y squared plus x over y minus 1, on top of this, and I can't really do that. But what I figured out, and I think it's kind of interesting, is that if you would think about it, the reason why we can't do this is if I have, like, say, the point 1, 2, this point right there,
And if I plug it in, that'd have a value, right? It'd have a value that may not have anything to do with this problem, but what we would have is for each point, like this one, there would be a numerical value of like, say, 1/10. This one here might have a numerical value of like 4. So what you've got is an XY placement, and then at each one of those placements, you've got a number. Okay? The way they deal with this in different situations is they color code things. Okay? So like different parts of your graph would have, it might be yellow because it's closer to 0, and then as it gets bigger, it gets more darker. And so sometimes, when you're trying to do 1, 2, 3 different variables, there's different numerical values all over the place. They might assign different colors for different ranges, and then trying to interpret what's going on. So that's what I was having problems with. But anyway, I don't know if that connects to any of you, but I'm trying. Okay? So any problems from last night you want to take a look at before we go on to our topic, the day? And we might get through a couple topics of the day. I don't know. Going all right? Okay.
But where it's just like, so when we do our like tangent and normalize,
Mm-hmm.
you just leave it as like the y minus.
You definitely can.
Or do you want to
If you want to simplify it to get it y equals, you definitely can. That's not a problem. Okay. The only reason I left it that way is because sometimes textbooks leave it that way on the ACT. Sometimes they leave it that way, and also I was just trying to decrease another step for you. And since Desmos will graph something like that, if you just type it in, it's totally up to you. Good question. Okay, so today I'm hoping that this kind of hits an interesting nerve for you today. And this is actually, I have no idea how long this is going to take. We might have to come up with something later. But you might remember that I asked at one point in time what the next numbers in this sequence is. Do you remember what the next number was? 8. Okay, 13. 21. Okay. So this right here is called the Fibonacci sequence. Fibonacci numbers, we can just call it that way. I'll tell you what, you don't have to write anything down today. You just help me, okay? Because actually, what we're going to do is never going to be on a test or something. If you like writing things down for your own personal enjoyment, you can. I'm not going to stop you, but I'm just trying to communicate that this is just an exposure, and I just want to show you some different things. So this is Fibonacci numbers. Here's what I want you to realize, and I want to investigate something. I want to investigate the quotient of any two consecutive numbers in Fibonacci sequence. Okay? So, for example, if I take 2 divided by 1, I get 2. If I take the next one, 3 divided by 2, I get 1.5. Okay? I want you to keep doing that for a while and see if you see a pattern. Go for it. And while you're doing that, I'm going to see if I can find a YouTube video to wrap this all up while you're investigating those proportions. There's so much neat stuff about this. This is cool. Are you noticing anything? Okay. Does it seem to be what's called converging to an overall number? Yeah, it seems to be about 1.6. So if I go 5 divided by 3, I get 1.6 exactly. If I go 8 divided by 5, I get 1.625. If I do 13 divided by 8, it gives me, 1 point. Oh, no, this is 1.6 repeating. This is 1.6. This is 625, right? And then 21 over 13, what is that one? Okay. So what it's doing is it's bouncing around a little bit. So imagine if you had whatever it's converging to 1.5. 1.6 repeating. The next ratio is 1.6. Next one's 1.625. It's getting closer and closer and closer to some value of some sort. Okay? And this value is a very special value. Okay? Let's do a couple more and we'll see if we can get a little bit closer. What'd you get for the next one? 34 over 21. Okay, thank you. 55 over 34. 1 point. Okay. So it seems like we're converging to some value. Okay? And that's an important idea in calculus later on is convergence or divergence. Divergence is when it does not get closer to a value. It starts getting farther and farther and farther away. Where this one, it's converging to a certain value. Okay? So here's what I want to do. I'm going to use a word that's going to strike fear into your hearts. I want to prove that this ratio is about 1.618. And I want to find out what that exact ratio is. And it's a very important ratio. Okay? So here's what we're going to do. We are going to, first of all, I will probably start, actually I think I can fit it over here. Okay. So here's what I want to do. If I had numbers that are in the Fibonacci sequence, that one is M, the next one is N, what would the next one be? Well, remember how we did this? It'd be M plus N, right? So what I want to prove, here's what I want to prove. I want to prove M over N is about 1.618. Okay? This is really a neat proof. And this is one of the things that that I think really shows you, ooh, we can do kind of some neat stuff. So here's what I'm going to do. What we know about this situation is M plus N over N. We're saying that these ratios are the same. So M plus N over N equals what? Not numbers-wise, in terms of M and N. So N over M. So we're saying that this ratio is basically gets to be the same. Okay? So if I take the next term over the previous term, that ratio is going to be the same as N over M. Okay? Okay. So, let's solve this. What would you do if you were going to solve this? I want to solve it for M. I want to solve this for M. And this is something you probably have never seen done before. But let's cross multiply. Cross multiply you've seen before. I'm not saying that. Okay? So if I cross multiply, what do I get? Help me out. What? M squared plus Mn equals N squared. Okay? Okay. So now what I'm going to do is I'm going to change what I said before. I'm going to solve this for n. I want to know what n equals. Okay. This is where I think it gets cool, and you probably haven't seen this before. Let's go ahead and get everything over to this other side, and you'll see where I'm going here real quick. 0 equals, help me out, n squared. No, I got to move it over. Minus mn minus m squared. Agreed? Okay. So now to solve for n, solve for n, well, let's back over here just a second. If you had some ugly quadratic, 2x squared minus 7x plus 2 equals 0, what the heck, let's make this a 3, and you wanted to solve that, and say it wouldn't factor, what would you use? You'd use a quadratic formula, right? The quadratic formula you would use is, you'd find x equals negative b plus or minus, help me out, square root of? Negative b plus minus square root of, see if anybody remembers.
No, it's b plus something.
B minus 4ac, b squared minus 4ac all over, no, 2a. So there's my quadratic formula, okay? And yeah, it's been a while. So that's why, we need to have those strength and connections. We'll bring that back up to your brain and see if your brain goes, ooh, I remember that. So basically, and you guys know that this value there is my a, whatever I'm taking times my squared variable. Whatever I'm taking times my variable itself is my b, and then my last thing is my c, right? Okay. So usually what you're used to doing is you're used to doing this in terms of just one variable only. I'm going to try and stretch you, and we're going to do this in terms of 2 different variables. Okay? So let's go over here. I want to do n. So what's my a? 1. I totally agree. What's my b? Negative m. Perfect. Okay? What is my c? Negative m squared. Okay? So now we're going to go ahead and use quadratic formula with those values of a, b, and c. Okay? So here we go. So n equals, I'm solving for n. Just like over here, I solve for x. Help me out. Using your formula. Opposite of b. M plus or minus the square root of negative m squared, which negative m squared is just going to give us m squared. Beautiful. Minus 4 times 1 negative m squared. Nice job. I like all your help. Over 2. Yeah, just 2 times 1. Okay, now I'd like to simplify this. N equals, well, m plus or minus. How could I simplify everything underneath the radical? In other words, it's called my discriminant. What's my discriminant in this case underneath my radical? What could I do? 5m squared. It's 5m squared. Because my negative and my negative cancel each other out, and we get m squared plus 4m squared. So we get 5m squared over 2. Okay. Do you think I can simplify this a little bit? Well, m plus or minus, I can take this m out. You okay with that? Technically, it would be the absolute value of m, but m's positive because it's a number in Fibonacci sequence. Okay? So I'm going to take this m out. And what do I have left? 1 plus or minus square root of 5. Okay, grab your calculators, please. Oh, we're not done yet. We're not done yet. Our goal was to prove that in this case, I wrote it wrong. N over M. N over M is 1.618. Okay? Yes?
Down at the bottom,
Mm-hmm. Yeah.
when you took out the M, why did the parentheses go around the whole thing and not just the top?
It did. I could just do the top, but I just pulled it out of the whole thing just to kind of get you guys set up for the next step. Okay? But either way, I could have, maybe I'm pulling an M out of the top and a 1 out of the bottom, and I'm just, so, but you'll kind of see why I'm doing that here in just a second. I could have done it that way instead. Okay? And it would have worked out the same. So my goal was to show that N over M is equal to 1.618. So, what should I do? Divide by M. N over M equals 1 plus or minus the square root of 5 over 2. Grab your calculators, please. Figure out what 1 plus the square root of 5 over 2 is. 1.618. Okay? Now the minus doesn't really have any impact here because it says the ratio is going to be negative 1 point something. The ratio is never going to be negative because all these numbers are positive. I got this fly. I'd love to demonstrate the best way to kill flies on live TV. Come on, land right here. Come on, dude. You know you want to. You know you want to. Anyway. So here's what we did. Was we saw a pattern. We thought, you know what? That pattern's always the same. And then we solved and recreated that fraction. And yeah, it is approximately 1.618 blah, 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 blah. That's a very special number. It's a very special number that's very much like E. It's an irrational constant, 2.718. Okay? Or like pi, the irrational constant that you can multiply a diameter by to get your circumference is 3.141598. Blah, 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 blah. Okay? So this is another number that is called phi, which the way to write that is, that's probably not the prettiest one, phi. That is a Greek letter, phi. Okay? So, you guys are like, yeah, big deal. What's the big thing? I don't really quite get it. It's kind of neat that we can use, first of all, it blew me away first time I saw that we can use quadratic formula with different variables and find one variable in terms of another variable. I just thought that was kind of cool. But I kind of want to get back to something what the kind of the purpose of this whole thing is. It's called the golden ratio. The golden ratio has been around for a long time. It's been around for a super long time. One of the most common uses of the golden ratio or observations of the golden ratio is in the drawing of rectangles that are pleasing to the eye. For example, if I would take and say this is 4 and that's 1, is that a good looking rectangle? No, it's not. It's too long. It's too skinny. It's just not good. Okay? But if we build something that is using the golden ratio, where this might be 8 and that might be 5, now that's a good looking rectangle. Okay? And this is back in the day when, if you look at any of the structures built by the Greeks or the Romans, they always used the golden ratio in their buildings. always, because they thought not only, I don't know if they had figured this out yet. I did have to do some history on the Fibonacci sequence and the actual discovery of it, but they wanted everything in the golden ratio all the time. Okay? And the golden ratio, outside of Fibonacci sequence, here's what it is. It's the sum of the two sides divided by the long side. So if I take these, where actually, in this case, 8 divided by 5, the long over the short is the same as the sum of the two over the long. That's what the golden ratio is really technically defined to be, is that you have in a rectangle, long over the short is the same thing as the sum of the two over the long. And let's see how accurate this is in this case. 64, is it equal to 13 times 5? 65. Yeah, that's a pretty attractive rectangle. That's what they decided. Okay? And so if we would take a look at a different one, I'm just going to come up with some ratio, some numbers out of the blue. 30 and 19. Let's see if the golden ratio holds in this particular problem. You help me out. 30 over 19 equals 19 plus 30 over 30. So 900, how much is that equal to? How close is that equal to 19 times 49? I know you guys got your calculators right there. April's all over it anyway. 931. So it's a pretty attractive triangle, or a rectangle. Where if I would do something like the ugly one we talked about before, 4 and 1, 4 over 1, how much is that equal to? 5 over 4? 5, 16? No. Ugly rectangle. Very. Okay? So this is kind of where the golden ratio, a couple things where the golden ratio was used. And it actually has lots of different applications in nature. So here's what I'm going to do. I'm going to pull up a video, and I'm going to try and, let's see, how can I do this? I'm going to have to, so that is going to go there. Okay, I can do this. I can do this. Okay, I don't want to disconnect that. I want to, okay, hold on. Let me get reorganized here a little bit, because I want to record for Willa. So anyway, while I'm doing this, maybe you have you ever seen quadratic formula used with two different variables like that before? And I think it's kind of cool. It really expands what we can do, and what the possibilities are. And part of you guys, I know you're probably thinking, I just hope I never have to do that. But it's kind of cool. Okay? Okay, so what am I going to do here? So this is feeding that. So smoke them if you got them for a couple minutes.
I mean, if you say so.
I've always said that. I could just see if that's some... Oh, no. Okay, so how am I going to do this? You know what I might do? I'm just going to go ahead and include the YouTube link in
in the video instructions. You know what I mean? Is that what you were saying? Yeah. Okay. Yep. Okay. Go ahead and let's get the door shut. I did not preview these at all. I was working on something else for another class. Let's get the lights. And I think my Bluetooth should be hooked up. Okay, and it's not. No, leave this light on, please, if you would. There we go. Thank you. Yep.
That's how it is in every room, but it's right above like where the teacher stuff is. Well, what if the teacher moves their desk? Then one random student gets blessed.
That's true. That's one thing where like when I was setting up my room, I had to meet with Mrs. Abrahams so we could talk about where I wanted this, where I wanted outlets, and this, that, and the other, and where I wanted my screen, and for what it's worth, there's a very specific reason why I set my rooms up like I do. Right now, if your eyes are here, you're not paying attention to what's going on in the hall. Okay? If I'm here, I'm facing you as you come in the door. I can greet you as you come in, right? So I know you're coming in. Also, if a student in my class wants help, they won't come up to the front of the room very well. How come? Say if my desk was here. Because what?
You're scared.
Scared of what?
Of like people like wondering why they're asking questions.
Exactly. So desk is in the back of the room. Those are just things those would kind of guide my philosophy of how I set up things. So anyway.
It's most conceptually difficult. Humanity has always been in search of patterns. They make us feel comfortable. They give us meaning. Whether they be on the deepest, most conceptually difficult topics like string theory and quantum mechanics, or even in simple things like the behavior of the person we're talking to. We love to see patterns, and do so sometimes against our better judgment. Nature and mathematics are no exception to that list when it comes to pattern seeking. In fact, it's at the forefront of it. We've evolved to notice patterns and be alerted when something isn't right. One of these so-called patterns that has fascinated mathematicians and individuals alike for centuries is the golden ratio. Also known by the Greek letter phi, it can be defined by taking a line and breaking it into two separate pieces. If the ratio between these two new portions is the same as the ratio between the original line and the now larger piece, the portions are said to satisfy the golden ratio. The value that satisfies this equation is roughly 1.618. It's an irrational number, meaning we can't represent it using the ratio of two whole numbers. In fact, we can't even write the number fully. It's unending. It's effectively the same as pi in that regard, and so we use the dots to represent the non-terminating nature of this number. But what makes this ratio so golden? The golden part of the name is rather modern. The more original name that was given to this ratio was the divine proportion. And right away, we can see that the term implies some sort of divinity, an extraordinary property that people must have noticed when they were dealing with this number. To further explain this fascination, we should begin by dividing the fascination into two parts: mathematics and aesthetics. The golden ratio and the Fibonacci sequence appear in nature every day, and arguably the strongest evidence of goldenness in the golden ratio is in the floral arrangement of seeds. Take this for example. If you were a sunflower, how much of a turn would you make before you made a new seed? It's a weird question, but it's an important one. If you don't make a turn at all, will you just continue making a straight line of seeds? That's kind of boring. If you make half a turn, or a 180-degree turn each time, well, now you have a line of seeds, but in opposite directions. 120 degrees gives you 3 lines. 144 degrees gives you 5 lines. There should exist some angle, some number of turns that, if properly executed, produces a pattern of seeds that is closely packed together with no gaps between them. Something like this. This seems more natural than nature, right? The number of turns needed to produce a spiral design like this is, well, the golden ratio. One seed placed every 1.618 turns, or every 137.5 degrees. This is known as the golden angle, and it is seen throughout all of nature. The idea is to arrange seeds in a way that can maximize the sunlight and rain that they receive, so that the genetic material can successfully be passed on to the next generation. If you don't do this efficiently, evolution won't be very kind to you. If you pack in the seeds too tightly, all the seeds won't get the nutrients they need. If you pack them too sparsely, you're just wasting space. This happens with not only sunflower seeds, but in plant leaves, tree branches, and even more. In fact, it goes even deeper. If you were to count the number of spiral arms in both directions, left and right, you'll find that they aren't equal. However, they will both always be Fibonacci numbers. The higher and higher the numbers go, the closer and closer the ratio between them approaches phi. The beautiful spirals that result are purely a creation of nature. These spirals are consistent across different flower types, and even the number of petals seem to be related to the golden ratio. The sunflower example is particularly interesting because it actually ties the aesthetic element of the golden ratio into the mathematics behind it. There's a reason why the golden ratio is used in flowers, and any other value doesn't seem to work very well. But what does that really tell us about the underlying and possibly grand design of the universe? We're all somewhat familiar with the aesthetic elements of the divine proportion. The idea is that visually pleasing faces tend to have proportions that are somewhat close to the golden ratio. The closer you are to it, the more beautiful your face should be. This inclination of harmony extends to the rest of the body as well.
Don't look.
Claiming that the chief truly man demonstrates that the human body owes its beauty to the golden ratio. The phenomenon also has its place in architecture, with claims done around the structures as old as the pyramids of Egypt are in some way, shape, or form inspired by the golden ratio. Except for the fact that there's hardly any evidence that the Egyptians even knew this ratio existed. All of these beliefs contributed to the idea of the golden ratio and made it what it is today. The mathematical beauty is undeniable. Its structure is as old as
I want to share some information about this structure with you. This structure is the Great Pyramid of Khufu. It's 480 feet tall. So imagine a football field is 300 feet. So it's a football field and 2/3 stood up on its end. This right here is 750 feet. They are ginormous. They're absolutely huge. This one right here uses 2.3 million blocks, each block weighing between 2 and 3 tons. To build that over a 20-year span, they would have to cut, move, and set over 300 blocks a day for 20 years. That's an amazing deal. It's just nuts.
Each are in some way, shape, or form inspired by the golden ratio. Except for the fact that there's hardly any evidence that the Egyptians even knew this ratio existed. All of these beliefs contributed to the idea of the golden ratio and made it what it is today. The mathematical beauty is undeniable. It's proven. However, it's generally hard to verify any of these claims regarding its aesthetic purpose in our lives. For one, it's not sufficient for a structure to just have the golden ratio somewhere. It must be meaningfully incorporated and be the result of someone's conscious or subconscious choice. But what does meaningful incorporation entail? Why would you choose the ratio of, say, this pillar with that one and not with another? And then there's questions of measurement. Oftentimes, you see pictures thrown around the internet with a famous celebrity's face with random lines drawn on them that claim to satisfy the divine proportion. Long story short, they're reaching pretty hard.
Imagine being able to build anything just by thinking about it. Meet Base 44, a complete AI creation platform.
I should have done this on my own personal YouTube account, which I've got no ads.
Without proper definitions of the facial features they're referring to, like what a cheekbone is, what it starts and ends, and so on, there's basically no scientifically verifiable structure to what they're claiming. Even if you do find that a certain arrangement and placement of measurements do wind up representing the golden ratio very well, it's never quite exactly that. Despite these claims, however, One could still argue about the idea of facial beauty in the...
Actually, one of the things that that they've really attributed beauty to is symmetry. If on your left is the same thing as on your right. Okay? You guys are getting restless. Is it time to go? Okay. Okay. I just wanted to make sure.
So the golden ratio, and all that matters is our perception of something. If the ratio of some facial features...
Okay, I don't know if I'm liking
so much so that we're
the rest of this.
The actual ratio itself, and we find it pleasing, there is some deeper meaning, deeper inside us. There's a body of research that focuses instead on deeper biology and how the golden ratio plays a crucial role in it. The cardiovascular system is of keen interest in this regard. This is because it's one of those biological systems that has very small differences across ethnic groups. So, if the golden ratio were to be found in such a system, we could claim that it is indeed a more universal phenomenon, rather than existing simply due to some ethnic variation or bias. The cardiovascular system is deep within us. It runs our lives. There is no element of fabrication down there. Evidence found here would much better support the idea that there is some natural significance to the golden ratio. And in fact, there is. Your heart has many moving parts that help keep your body functioning. One of them being the left ventricle. Is what helps pump oxygen throughout your body. Now, the average ratio of left ventricle horizontal and vertical lengths of over 1,400 Swedish and Chinese subjects was found to be 1.618, awfully close to the golden ratio. Patients with left ventricle ratios that were further away from this value were deemed to have poorer functioning hearts. And as we age, our hearts tend to lose some of their power. Your blood begins to pump slower and slower throughout your body. Even the age-related cardiovascular decline was related to the golden ratio, with an early diastolic velocity decline of 1.6 centimeters per second per decade. On the other side of the spectrum, the early diastolic flow velocity of muscles in the heart of a growing fetus increases by 1.6 millimeters per second per week. It's remarkable how these and other metrics of cardiovascular health hover close to this special value. But even in these examples, there's still a bias in choice of units. For example, why is this particular metric in millimeters per second and not inches per second? Such choices could alter this.
I'll do a shorter one that just focuses on nature.
The sequence begins with the numbers 1, 1, 2, 3.
Sorry, I didn't preview that a little bit better.
13, 21, 34, and continues indefinitely. Each number is obtained by adding the last two digits together. If we were to take a perfect or golden rectangle, break it down into smaller squares based on Fibonacci's sequence, and divide each with an arc, the patterns begin to take shape. We begin to see Fibonacci's spiral. The spiral in and of itself is insignificant. Its importance is revealed in where we find it. Take, for example, the sunflower. The display of its florets are in perfect spirals of 55, 34, and 21. The sequence of Fibonacci. The fruitlets of the pineapple create the same spiral based on the sequence. The pine cone does the same. As currents move through the ocean and the tide rolls up to the shore, the waves that bring in the tide curve into a spiral that can be mathematically diagrammed onto a plot at the points 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55. Buds on trees, sand dollars, starfish, petals on flowers, and especially the nautilus shell are formed with this exact same blueprint. With each segment of growth, the nautilus adds to itself one more value on Fibonacci's scale. This blueprint can be seen around us on a small scale every day, but the greatest example of all is directly above our heads. At an average of 100,000 light years across, even the spiral of the galaxies above us are formed with the exact design that the tiny shell is formed. This sequence or blueprint appears to be the trademark of a designer.
Okay. So anyway, there's, what time are we looking at? 8:49. Ooh, it is 50, isn't it? Okay. So, I just think there is so much elegance buried in mathematics that I hope to kind of share that a little bit with you here and there. And there's a lot more about Fibonacci sequence I could share as well. But if you're interested, check out the golden ratio a little bit more. Anyway, hopefully you found it interesting. Have a great weekend. Thank you. Oh my gosh, that's bright. Okay. That's a calculus problem I'm trying to figure out. No, it's not for you guys. I'm just trying to figure out that calculus problem. Okay. I'm going to spend some... Okay. I have got some students that are going to be gone all next week. So I'm going to take some time right now to get next week really ready so I can just tell them this is what we're doing. Okay? So the large majority of this period, maybe all, is going to be on your own. We're doing something a little different in class today anyway. So you are... I'll probably get some music going and you guys can... Yes.
Are you going to have me take the test since I've been gone the last 2 days?
That's a retake.
Oh, that's a retake.
Yeah, those are retakes. So there is
So
no...
we don't have... Oh.
No.
I thought you said we were going to...
I changed my mind.
Okay.
I changed my mind.
So we're going to... Do you know when we're going to take it?
It'll be next week. Next Thursday, actually.
Okay. Sounds good to me.
Just you, cowboy.
So you don't write in the please, the Spanish thing. I thought you were going to do it.
Yeah, I did.
Like the please.
Oh, I didn't write please. Oh, if you want to add it, you can. Okay. This book, it just drives me bonkers. It just drives me bonkers. Por favor.
It's Mark's bar. She left it in my room.
Okay,
Shower.
great. Thank you. I'm always freaked out when people are speaking a different language because then I think they're trying to hide the fact they're talking about me.
It's like when you go to the nail salon and they're speaking Chinese.
Oh,
Yeah.
They could be talking about I was just asking her about...
You don't have to explain it. You don't have to explain it. I'm just trying to make a joke. I'm not worried about it. And do you guys think in Spanish or English? Spanish.
Yeah.
Okay.
Both.
Yeah. So, if that's what you think in, it'd be a lot easier to talk in that rather than have to, so.
That's interesting.
Yeah, it is.
We can both.
I think it's very interesting. Okay.
Yeah, and since I practice It sounds better in my head. Then when I say it, it's really bad.
Okay.
Entonces lo que quiso hacer, era uno que tenía muchos problemas y que tenía A, B y C, como ecuaciones A, B y C.
Okay. I'm.
Do you have any extra copies of the worksheet that you guys were working on yesterday? The one with the ABC equations?
It's right there. Not that one. Nope. The other one. There you go.